Everybody. So we're going to kick things off with question one. So question one is just a bunch of short questions that evaluate understanding of a whole variety of topics that we've discussed this semester. So let's start with number two, because I just filled out my honor code signature. This was given in online format. And so kind of like the PDF version that we've compiled here isn't really representative of what the actual exam would look like. But that's just from a graphical standpoint. Okay, so number two, it says having a pipeline with more stages will always, sometimes, or never decrease the overall execution time. Okay, so the way I like approaching these problems is I try to find a scenario where this is true, find a scenario where it isn't true. If I find both, then it's sometimes, if not, it's always or never. Okay, so having a pipeline with more stages will always, sometimes, or never decrease the overall execution time. So the example that comes to mind with regards to where this statement is true, is a single stage pipeline, right? A single stage pipeline is essentially just a single cycle processor because you're not doing multiple things in parallel. And we've seen in this class multiple instances where our 5-stage pipeline performs significantly better than our single stage processor because it allows us to parallelize instructions. And you can also get lower clock speeds, right? But this is an example where it is true. So I can kind of cross out never. Okay, so now let me see if I can think of an example where this is not true. Well, just intuitively, it seems like there would be situations in which this would not be true, strictly because if it were true, I would just make a pipeline that was like thousands or hundreds of thousands of stages long, right? I could break it down as small as it could get. But obviously this isn't what happens when people manufacture chips, and it's not just because of cost. And so that's kind of like the initial reason I think it's probably going to be sometimes. But as for why it actually is, there are the more you split up your pipeline, the more chance you have to introduce hazards, right? So there's data and control hazards, and those hazards become more and more significant in terms of the number of cycles that you have to stall. And so at a certain point, you start breaking up your pipeline, and you introduce a ton of hazards. Additionally, right, we had problems where we talked about how increasing the length of the pipeline increases the propagation delay on certain wires. And so all of a sudden, a signal takes really long time to get from, let's say, the last stage to the first stage. So this answer is probably going to be sometimes. Cool. So number three says, given the same set of instructions, a pipeline that uses detect and stall will sometimes perform better than a pipeline that uses detect and forward with speculate and squash. You can assume that both pipelines have the same clock period and are identical in every way, except how hazards are handled. Okay, so essentially this question is asking us to compare detect and stall and detect and forward. And it says that detect and stall will sometimes perform better than detect and forward. Well, this is simply not true. Now, the reason for that is, let's go back to what detect and stall are and detect and forward are. So detect and stall is the data hazard resolution technique that we use, which essentially is implemented in hardware. And essentially what happens is the architecture sees that an instruction is about to complete that is going to, for example, overwrite a register that is used in the next step. And so in the next instruction. And so essentially what it does is it just says, hey, instruction that needs the values, you're just going to stall, right? I'm just going to insert a bunch of no ops, essentially, until those values resolve, right? Until those values are completed, getting calculated in the ALU. And then at that point, it allows it to start running. The problem with that is kind of like that stalling takes a couple extra cycles. So detect and forward was the data resolution technique, where it would see a similar occurrence, right? It would see that a prior instruction is going to overwrite the register values in the future. But what it allows the pipeline to do is replace those values with the correct values later on in the pipeline. And what that allows it to do is insert less no-ops, right? There's less instances where you have to insert them, because if I don't need the values yet, I can, wait until they are replaced, and I don't necessarily have to get them from the registers. So detect and forward, the reason this is false is detect and forward is almost strictly an improvement on detect and stall. It just says, if it's possible, I will forward you the values. If not, you're going to have to stall. But stalling is kind of the worst scenario. And so detect and forward is always going to be better. So this is going to be false. Moving on to question 4, it says a pipeline that uses speculate and squash to handle control hazards would have 0 squashes if all branches are predicted correctly. Okay. Okay, so what is speculate and squash? So speculate and squash is our control hazard resolution, and is a form of it, and it allows us to kind of guess whether a branch is going to be taken or not. If we're correct on which branch is taken, we continue to execute the correct instructions, and it's all good, right? And I have 0 stalls. But if it turns out later that once my branch instruction finishes executing, it turns out that my guess, my speculation was wrong, then I have to go and essentially squash, which is go through all of the instructions that I started executing that shouldn't actually be executed because they're the wrong instructions. And I need to go cancel them, essentially. I need to go turn them into, essentially just go and turn them into no-ops. And so this question is asking us, what if we were correct every single time? Well, we're going to have 0 squashes, right? I'm always going to execute the correct instructions. I'm never going to execute the incorrect ones. So I never have to squash. So this is going to be true. Cool. Caches are an important part of computers because they generally store more memory relative to the hard disk and have very little latency. This is going to be incorrect. And the reason for that is, while it is true, caches have very little latency, right? They're really fast. It's great. They don't store more memory. Remember, going back to like what we talked about in lectures, we had this visualization of like this pyramid, right? In the very top, we had like our registers, and those things are really, really fast. And they have very little memory, right? Each of those registers might only be 3264 bytes. And below that, we talked about like the cache, and we said the cache is also really fast, but again, it's not going to be able to store all the memory I need. And so then below that, we had memory and then disk, and if you're really going for a stretch, you have like distributed system, like distributed storage and such. But the main idea was at the very top, we had very fast but small memory. At the bottom, we had much more expansive but slower memory. So this is incorrect because it says it has more memory. So number 6 says a fully associative cache will always, sometimes, or never require more tag bits per entry as the cache size gets larger, given that all cache sizes are powers of 2. Okay, let's think about what's stored in a fully associative cache, right? Well, because it's fully associative, I don't have like set divisions. So essentially, I'm just going to have one LRU. And so in addition to the LRU, I'm going to have more, perhaps like maybe like a dirty bit. But the main idea is that I never store my tag bits in my entry, right? My tag bits are or sorry, I do store my tag bits in my entry, but like they're not going to be any sort of overhead. That is the core storage of the cache. So if my cache gets more entries, right? I'm not going to change the size of each entry. The only thing that might grow is the LRU, right? The LRU is proportional to like the log of the number of entries. But every other, as far as I know, every other part of a cache entry is going to be corresponding to like a static number of overhead bits plus the tag bits, right? So the answer to this is going to be never, because growing the number of entries doesn't affect tag bits. Tag bits are affected by, I guess tag bits would be strictly decided by the addressability of the system, as well as the addressability of the system. So if I had a 64-bit system versus a 32-bit system, I'd have potentially more bits in, or more tag bits in a 64-bit system, but also by the block size. But neither of these is changed by the size of the cache, and so this is going to be never. Well, so then it says a write-through cache will always, sometimes, or never write to both cache and memory. So remember, a write-through cache is a cache in which whenever I perform a write to the cache, I will both update the cache and the memory. So this is one that got a couple people. I remember when I was taking this exam, and so it seems intuitive that like the cache, the writing method that we use in the cache would directly correlate to what we described. It's almost by definition. However, the reason this answer is going to be sometimes instead of always is because this policy doesn't address what happens if something was not in, if I'm writing to something that wasn't in the cache. Let's say that something was in memory, right? It was never in the cache. And so there's two options, right? When I want to do that, I can bring the value into, or bring that block into my cache and then update it, and as well as update the memory, or I can choose to just update the memory. And this is the write allocate versus write no allocate policies, right? That's not determined by write through versus write back. Write through versus write back is talking about what if something's already in the cache and I'm writing to it. So, you know, if this was a write through and write no allocate system, then, and the value was not in cache, it was just in memory, then I would just write a memory. And so I found an example where I don't write to both cache and memory. So this is going to be a sometimes. So then it says a cache with very large block sizes will generally have less compulsory misses than compulsory misses than a cache with smaller block sizes. So what are compulsory misses? Well, compulsory misses are essentially misses that happen because that particular address had never been looked up, had never been brought into the cache. But we know that there's examples of instances where I've never looked a particular address up, but it exists within the cache. That example is, what if I had two addresses that belong to the same block, right? If I search up address 0 and address 0 belongs to the same block as address 1, and then I search up address 1, I'll get a hit on address 1, even though like maybe intuitively it would seem like something that should be a compulsory miss. So what we see is we can reduce the number of compulsory misses by ensuring that addresses are on the same block. For example, if I had a block, let's say my block size was massive, let's say it encompassed my entire system, right? So all the memory I could potentially address is stored within one block. And so I can store it all in my cache. But the first time I perform net address access, I'm going to get a compulsory miss. But from then on, I'm never going to get any misses, right? And so, yes, increasing the block size may increase decrease the total number of blocks that you're storing, and then as a result, would result in evictions. But in the main idea is it's going to result in less compulsory misses. Maybe not total misses, but this is going to be true. So then this question asks, it says SRAM will have higher costs to make, but will generally have higher latency compared to DRAM and the disk. So it is true that, SRAM, remember, is the memory that is used, tends to be a lot faster, right? And so that's what's used in like caches. But it is true that this type of memory is more expensive. But it says it will also generally have higher latency. So that's not going to be true. Remember, we're going to pay. Why would we pay extra money for a memory to perform slower, right? So our caches generally tend to perform with lower latencies, and so this is going to be false because SRAM has lower latencies. So then number 10 says the TLB lookup could happen in the pipeline after the virtual address is calculated and before the memory reference is executed. So just to clarify some of the wording here, so the TLB, remember, is a cache that allows us to more quickly translate a virtual address into a physical address. So with regards to the virtual address being calculated, this most definitely would be something that would happen before the TLB lookup occurs, right? Because I want my virtual address before I translate. And then when it says that before the memory reference is executed, this could essentially mean a couple of things. It could mean I'm looking in disk, I'm looking in cache, I'm looking in memory. But regardless, I want to say memory. When I say memory in general, by the way, I am referring to DRAM. So I'm referring to that sort of memory. But absolutely, the TLB, the translation from virtual to physical, is something that would likely even happen between these two stages, because I need to turn that virtual address into a physical address for me to look inside my DRAM. Like if I have a virtually addressed cache, then maybe I don't need to do that. But this question is asking us, can it happen? And that absolutely can. So this is going to be true. The last question in this part, it says the translation look-side buffer, again, the TLB, will often have a hit rate that is greater than 90%. So this is going to be true. It's kind of just something that we discussed in lecture, which is, and the reason that you're going to have such a high hit rate in TLBs is, one, all they store is a translation from a virtual page number to a physical page number, right? And that means the entries can be somewhat small, which means you can store a whole lot of entries. Now, although each of these entries are small, the virtual pages that they're representing are pretty big. We've talked about like size that I've seen frequently is like 4 kilobytes, right, for a singular page. And if each entry might be something in a 32-bit operating system, like 4 bytes, or I guess a little bit more, let's be lenient, call it 8 bytes, right? If I can represent a 4 kilobyte portion of my virtual memory with just 8 bytes, I can, chances are I'm going to be able to represent most of my translations inside my virtual, inside my translation look-aside buffer. And so that's why the hit rate's going to be so high. Awesome. All right. Hopefully you found that helpful. We'll pick up on number 2 in just a bit.